Thank you for the warm introduction. Good morning, at least from my time zone, and welcome to my talk. Next-gen smart cards need trustworthy post-quantum cryptography. My name is Lucie Plaga, and I am working in the hardware department at TÜViT. Next-gen smart cards need trustworthy post-quantum cryptography. I'm going to show you in this talk that it is possible to be secure against quantum computer attacks, even with classical devices, with classical computers, and this is the field of post-quantum cryptography. And the outline of the talk will be the following. First, I'm going to talk about the basics, why a quantum computer differs from a classical computer. And from this, we will look at the cryptographic schemes that are in use today, and I will discuss which schemes will be affected to what extent. And for the schemes that are not secure anymore in the age of quantum computers, there's already a solution available, and this is the field of post-quantum cryptography. These are new algorithms that can replace the existing ones, and I will show you that a variety of PQC algorithms already has been developed. When one thinks about the timeline and thinks about when to initiate the transition of replacing currently used algorithms with PQC algorithms, the timeline might be that one should start as soon as possible to be ready just in time at the day when the quantum computers are available. And fortunately, it is actually already possible today to start the migration to PQC because the algorithms that I talked about before, many of them are undergoing standardization processes, and some of them already have been recommended by governmental agencies. And the standards that are still needed are expected in between 2022 and 2024. On the last slides, I'm going to talk about the challenges one faces when actually implementing an algorithm. And this is the same for classical as for post-quantum cryptography, because an actual implementation also has to be secured against physical attacks, and it is not sufficient to just choose a mathematically secure algorithm for a product that actually is in the field. But first, let's look at the basics, and let's look at the differences between a bit and a qubit so that we might understand why a quantum computer can solve some tasks better than a classical computer. The building blocks of the classical computers are the bits, and a bit can have either value 0 or value 1. And this might be physically implemented. For example, a bit can be stored in a capacitor, and either the capacitor has charge inside, then this would be a 1, or no charge inside, then this would be a 0. So this is an actual physical implementation of a bit, but there are other possibilities too. And for the quantum computer, its building block, the qubit, is physically made of much smaller objects. So qubit might be as small as a single atom or even an individual light particle. And for particles that are that small, one has to take in mind the laws of quantum physics that only apply to such small objects. And this is why we will see this soon. The quantum object can be represented by this sphere, and a physical qubit also has a basis state 0 that can encode the 0 we already know from the bit, and also has a basis state 1 that can encode the 1 that we know from the bit. But on top, because of quantum physics, the qubit can be in an intermediate state, and this is called superposition, and it is schematically represented by this sphere with the arrow up corresponding to the basis state 0, arrow down corresponding to the basis state 1, but all states that in between are points on the surface of this sphere. And this results in a qubit being able to encode infinitely many values because there are different superposition states represented here by different points on the sphere and an arrow pointing to the respective state that the qubit actually has at the moment. But what one has to know is how qubits interact with the macroscopic world. What does happen when one tries to read out such a small quantum object? The quantum object is in superposition here in this picture, and it is in a superposition in between 0 and 1. But when one takes a look, this means measuring or reading out the qubit, one only receives either a 0 or either a 1. So the superposition cannot be measured directly, and this is called collapse of the superposition. By measuring, the qubit changes its state to either being in the basis state 0 or basis state 1. And it is a question of probability whether one receives the 0 or the 1. And this is why quantum computers only execute probabilistic algorithms that lead to the desired result with a certain likelihood. Superposition is powerful when it comes to encoding large input values. For example, when one tries to attack a cryptographic scheme and wants to test lots of keys, wants to test whether one can decrypt a message with a variety of keys. In the classical scenario here on the left, I have depicted a single bit. So in the left box is the state where this single bit is 0, and in the right box there's the state where this single bit is 1. For a classical computer, if one wants to evaluate a calculation with both, then one has to do the calculation twice. But this is different for the quantum computer because the superposition of 0 and 1 can be used to encode 0 and 1 at once. So on the left, 2 executions, on the right, potentially only 1 execution of the algorithm. And this becomes even more powerful when the number of bits in the bit string gets higher. For example, here, if one wants to consider 2 bits, they can have the combinations 0, 0, 0, 1, 1, 0, or 1, 1, but only one of the combinations at a time. So to test all 4 combinations, an algorithm would have not to run 4 times. But for a qubit register, this is not true because 2 qubits can be used to encode all these states at once. And this is scaling up. So for example, what you can encode in 6 qubits, this corresponds to having an algorithm run 6 times. To the power of 6 times, I'm sorry. So this is scaling up a lot. And with this property, it is possible to construct quantum algorithms that need less executions to get to a result than the classical analogon would need. On top of superposition, qubits also have the property that they can be entangled, and this means that 2 qubits can be put in a shared state, and then they act as if they were 1 qubit. Let's look at an example. So this is a shared qubit state of these 2 qubits, and let's think of this being the superposition state of either 0, 0 and 1, 1. So in superposition, but then when a measurement is done, let's remember that then the superposition state results in one of the basis states. And when the red qubit is measured, we can measure a 0 or a 1, but immediately the state of the second qubit, the blue one, is also decided, and it is also not in superposition anymore, although we might not have taken a look at all. And this still is the case when the 2 entangled qubits are separated, and when the distance is increased, then I can do a measurement on the red qubit, and because I know the 2 qubits are entangled, immediately know what the second qubit is. And this also has an application in cryptography because new key exchange protocols can be constructed from sending qubits back and forth and sender and receiver deriving the same sequence because the qubits are entangled. But in case of the quantum computer, entanglement is used to link several qubits together so that they form qubit registers. And when one has built such a quantum computer, the executed attacks might have a speed up for some very specific problems. And for example, one of these specific problems that a quantum computer can solve faster than a classical computer is a key search attack. And this affects symmetric cryptography. What you see here are two communication parties, Alice and Bob, and they have a pre-shared secret, a secret key that they might exchange when they met, or maybe they have a trusted channel on which they can share this secret key. And then Alice wants to send a message via an untrusted channel, and this is why she chooses to encrypt her message with the secret key, sends it to Bob, and Bob then decrypts the secret with a shared key. And a classical computer can attack such a scheme, for example, by taking the encrypted text and then iterating through all potential keys and trying to identify the one that actually decrypts the message. But for the schemes that are in use today, for example, AES 128, this is considered not feasible because the key sizes are chosen so large that classical computers would need too much time to decrypt this message just by going through all potential keys. But because a quantum computer can execute algorithms that speed up these key search attacks, a quantum computer can identify the key decrypting a message for today's key sizes. But the solution is not so out of reach because the solution to this is just to increase the key sizes. And this means in practice that essentially the key sizes that we have today need to be doubled in order to be secure against quantum computers. For example, today AES 128 is considered secure for most applications, but in the future we do have to upgrade to AES with 256-bit key size in order to maintain the same level of security. Because for larger key sizes, the speed up is there, but it is countered by the increased key sizes, and the same level of security is still provided even when this key search attack is executed with a quantum computer. However, the situation is completely different for the public key schemes that are used today, and the public key schemes that are most widespread today are the RSA scheme and also elliptic curve cryptography, and both are important for encryption and decryption, but also for the generation of signatures. And especially important because for public key cryptography, it is not necessary to have a trusted channel in the beginning to exchange keys. And this works in the following way. Here on the right, Bob, in the beginning, constructs two keys, the private key here on the right, and the public key depicted by this lock here on the left, both constructed by Bob. And these two share a certain relationship. The private key belongs to the public key, but only parts of the key are made publicly available, and Bob can distribute his public key in the internet. He can put it to the cloud, but he has to keep his private key secret. And Alice, who wants to encrypt the message, then takes this public key and encrypts her message with the public key, sends it to Bob, and Bob can decrypt with his private key. The other way around, it is possible that Bob signs a message and that Alice then verifies that it was indeed Bob who signed the message, because it is not possible for someone who does not have the private key to generate a valid signature. And you see here that no trusted channel is involved, and at the root of these are so-called one-way functions. These are functions that can be easily calculated in one direction. So this is encryption with the public key, but that cannot be inverted unless one knows a trapdoor, the secret key. And of course, public and secret key have a certain relationship, but it is not possible to get the private key just from knowing the public key. And the schemes we use today, RSE and ECC, for these schemes, they are one-way functions for classical computers. Unfortunately, not for quantum computers, because quantum computers can solve the underlying mathematical problem efficiently, and there are no fixes available that would prevent a quantum attacker from just calculating the private key from the public key for both RSA and ECC schemes. Fortunately, there is post-quantum cryptography, and the good news about post-quantum cryptography is that it allows us to keep public key cryptography, so that the same constructions with a private and a public key that is openly distributed can be kept, but that the underlying algorithms only have to be replaced, and they have to be replaced by algorithms that are hard to break for both quantum and classical computers. And fortunately, algorithms that are hard to break for quantum and for classical computers do exist, and they are based on different mathematical problems than the one that the quantum computer can efficiently solve. And here in red, I wrote down the names of different post-quantum schemes that are currently undergoing standardization processes or already have been recommended by governmental agencies for several use cases. And you might see from the sheer variety of schemes that there are lots of different schemes around. And it is also the case that we will have several schemes around in the age of post-quantum security. And this is because these schemes are only appropriate for different use cases. There is no one-size-fits-all algorithm that can be used for encryption, but also signature generation that can be used on devices that need a fast speed of end decryption and also have limited resources. So each of these algorithms has its drawbacks. For example, it might only be possible to construct a signature scheme with it, or it might be that key sizes are very hard. And this is why in the age of post-quantum security, it depends on the use case, which algorithm is suitable. And this is also for standardization processes that many algorithms will be standardized, and then developers have to choose the appropriate one for their use case. So when one thinks of when should I start to implement post-quantum algorithms, when should I start buying products that are post-quantum secure, then one could easily be fooled by the assumption that it is sufficient to wait until the day that a quantum computer really is available, that has the needed number of qubits to actually attack today's public key schemes. But of course, when this day comes and one is not prepared, then it is too late. And this is depicted in this graphic. We have here in red the time it takes until a quantum computer can execute powerful attacks, starting from today. And unfortunately, of course, the exact time frame is unknown. It might be 10 years, it might be 30 years, but from today, as rapid progress is made in quantum computing, one should think of it as eventually coming one day. And when one initiates the transition, there is a certain transition time, and this is the time one needs to develop the needed algorithms, but also to implement them and then to replace products that are actually in the field. And only after this, then there's a certain lifetime. This might be the lifetime in the field of the product, but it could also be that the lifetime is longer than the actual time the product is in the field, because even today, there is the possibility to copy data that is transmitted on the internet or stored in the cloud. And this information might be valuable 10 years from now. So if this is the case, then this information has to be secured today, so that the actual lifetime in which knowledge of the decrypted values might be valuable does not exceed the time until a quantum computer can attack these data. And transition time and lifetime are not easily influenced, because replacing cryptographic algorithms takes considerable time, and also the lifetime of the information is just what it is. So maybe the only possible thing that one can influence here in the overall picture is the time at which the transition is initiated. Because here is depicted the good case in which transition time and the lifetime of the information are not longer than the time frame in which a quantum computer can perform powerful attacks. And we are of the opinion that the transition can already start today. And this is also because standardization of PQC algorithms is making rapid progress. I showed you before several schemes, and these schemes are already condensed down from a standardization process starting in 2016, conducted by the NIST, the National Institute of Standards and Technology. And this is the largest standardization process that we see today. And the status this year is that 7 finalists and 8 alternate candidates from the field of PQC have been announced, and it is expected that standards are available between 2022 and 2024 for different use cases. And if one wants to start even earlier, even want to start tomorrow, or even maybe are currently already implementing PQC schemes, then a possible approach is to combine one of today's asymmetric cryptographic schemes with one of the new post-quantum cryptographic schemes, for example, for a key derivation that can be implemented in such a way that there are 2 key ingredients, one from the classical scheme, one from the PQC scheme, that together form the hybrid key. And such a hybrid scheme is compliant with current legislation, because the current asymmetric scheme is used, but also already preparing for a future in which this asymmetric scheme might be broken, but the post-quantum cryptographic scheme still stays secure. But now I want to come to the field of implementation security, because it is important to keep in mind that cryptographic security is not only mathematics, and that a product is not secure automatically when a standardized algorithm is implemented. And this is especially true if an attacker can get hold of the physical product, for example, in the context of smart cards, because there are a variety of attack paths to extract secrets from such a product, even by not attacking the actual algorithm, but by attacking the implementation. And one powerful class of attacks are side channel attacks, and they exploit that, for example, timing, power consumption might be data dependent, as well as the emanation in the electromagnetic field. Maybe there are acoustic signals, or even the device is heating up data dependently, and this can be used to extract secrets actually from such a products. And this is also my background and background of my colleagues, because we work in a hardware laboratory where we conduct such measurements. And here on the right, you see one of my colleagues extracting secrets from a device by measuring power consumption and emanation in the electromagnetic field. And then there's also the attack path of actually disturbing the calculation by inducing faults. And there are a variety of fault injection techniques, and they aim at extracting secrets from such a device, for example, by stopping the calculation before its actual endpoint, but then maybe retrieving secrets. And what we already learned is that post-quantum cryptography can be attacked just like classical cryptography, and this is depicted here in this picture. It is a timeline, and here one sees the number of publications dealing with attacks on actual implementations of post-quantum cryptographic schemes. And that the number of publications is rising does not mean that these schemes are insecure in principle, but it just means that the same attack paths already known for classical cryptography work for post-quantum cryptography. But the good news is that the mitigation techniques that are already known for classical cryptography also work for post-quantum cryptography. But it is important that one has knowledge of classical attacks, and that also testing of the actual physical product is conducted in order to estimate how secure the actual implementation is against physical attacks. And this was a very brief summary of our recently published white paper. It is out today, and I have attached it to the agenda. To this talk, in the agenda is also attached the recently published white paper, and I'd invite you to download it and to have a look inside if you are interested in more detailed information on all the topics that I covered today in this short talk. Thank you, and if you have any questions, I'm happy to hear them.